This is my presentation today. It's Cosmos at Work. So let's start. So the outline of today's presentation is going to be like, it's an interesting topic. It's a big topic, but I've tried to crunch it to the level possible to the audience given the time frame. So the key questions that I'm going to answer at the end of this presentation, by the end, is like these questions: how did the universe start? How are stars formed? How long do these stars live and their life cycle when they die, and what happens when they die? And what's the connection between a star, and all of human life? And how do we track this life cycle? So these are the topics that I'm going to cover today, in a nutshell.
Something small.
Yeah. So we are going back in time here, billions and billions of years. I don't have a numeric number, but this is where the origins of the universe started. So it's basically one giant chunk of matter, if you see here on the far left of your slide. What happened was, as time evolved, there was some reaction taking place. So what happened was these giant chunks actually began to break down into smaller particles. By smaller particles in astronomical terms, I mean galaxies and some other things bigger than galaxies. They are big chunks. So this is what is called the Big Bang theory. The Big Bang theory states how this solid chunk exploded into several smaller chunks. So this is a logarithmic scale. That's the only way we can present this. So it cannot be scaled linearly. So we have to present it in a logarithmic format. So going to the next slide, this is what you see in the night sky. I want to ask the observations made by you here on this current slide. So what do you see on this slide?
Lots of stars.
Yeah. So lots of stars, bigger, smaller, different colors. Why are they in the state they are? Any guesses? Why are some small? Why are some big? Why are some red? Why are some white? Yeah. 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 It's a combination of everything. It's a combination of temperature. It's a combination of distance from us in terms of light years. And it's also telling you the apparent size of the star compared to our reference point of the Earth. So basically, stars have different colors, they indicate different temperatures, different sizes, different masses. The bigger it is, the hotter it is, and the faster a star burns, it actually perishes. So that's what we saw in the previous slide. So let me go on to the origins. So what you see here is Eagle Nebula. This picture was taken from the Hubble telescope. It again tracks to the origins of the universe. There you can see a large chunk of clouds there, and also you can see some stars. So essentially what happens is, when the universe began, you had only a few elements. We didn't have a lot of elements we have today in the periodic table. We only had 3 elements, to be precise. We had hydrogen, traces of helium, and lithium. So these were the only 3 elements.
What was the third?
Pardon?
What was the third?
Lithium? So essentially they were in the form of clouds. So these clouds were formed during the Big Bang. So basically these clouds consisted maybe of 90% hydrogen. Maybe the remaining 2 elements constituted the remaining percentage, I would say. This is also a shot from the Hubble telescope. It's called the N81 nebula. So moving on. So what happens is when you have a very dense cloud of hydrogen gas, it tries to actually form into a very dense environment. So it kind of compresses into a volume of a sphere or something like that. That's where I think the star begins to start, because there are different masses within the cloud, and the bigger mass will attract the smaller masses. So we will have a natural force of gravitation going forward. The first cycle of the star is called the protostar. This is where the gravitational attraction takes place, and then the star is actually in its infancy. It's kind of being born. So what happens as gravitation takes place is that there will be contraction, and due to contraction you will have a rise in temperature and pressure. So what happens here is very interesting. Due to the temperature and pressure conditions, we have a nuclear fusion reaction taking place. Nuclear fusion reaction is nothing but you have hydrogen molecules. 4 hydrogen molecules fuse together to form one helium molecule, and in the process a lot of energy is emitted, radiated. So we are talking about 15 million degrees Celsius. So on Earth, we cannot achieve fusion that easily. For a man to make a fusion reaction, he has to make a fission reaction first, and then take that heat and then create a fusion reaction by chain reaction. So that is the volume of effort that is required to initiate a fusion reaction. So as I said, 4 hydrogen atoms will form one helium, and then 2 neutrinos, and there is an electron, but it has a positive charge. If you see that, it's called a positron, and energy. So this is the chemical reaction that's taking place. So where does this energy come from? So it's because of the fusion reaction, and this is the equation that's responsible for the energy, E equal to mc square, which is a very famous equation, Einstein's famous equation. So how much energy are we talking about here? We are talking about 25 MeVs. That means it's the energy for moving 1 million electrons through 1 volt. So that's the energy we are talking about. We can also represent this in calories or joules. So the point is, this happens 10 to the power 38 times a second. So it's like, if you talk of power, then it's W by T, work done by time taken, so energy by time. So it happens at a fairly continuous rate. 10 power 38 times a second is like a huge amount of instances within 1 second. So, for example, I'm taking the sun here as because it's our closest star and the star that's most relevant to us. I'm taking sun as an example, but it pretty much applies to any star. So our sun, for example, is not a very big star in astronomical terms. It's just an average size star, and that itself has 10 power 56 hydrogen atoms to burn. By burn, I mean available for fusion. So it's a balancing act. So what happens is, every time a star has to fight against 2 things. One is the energy delivered and this gravity itself. So whenever one overcomes the other, there will be a catastrophic event. So if there is not enough energy radiated, then the gravity will take over and the star will get destroyed, because it will collapse by itself. It will implode, it will not explode. Implode before exploding. We'll come to that. So what happens is, like, for several billions of years this reaction takes place, and then we get the radiation out from the star, and that's what you're seeing for several billions and billions of years. But then it doesn't last forever. So what happens is, they will gracefully die, or catastrophically die. Two ways, and it depends on the size of the star. So there are two kind of scenarios here. If you see there, I'm taking Sun because Sun is a pretty average star, average size star. We'll see what happens with the Sun, and we'll also see about massive stars, which are very 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 big and emit radiation like in the white band or the blue band in terms of temperature. So let's take our Sun for example. So maybe from 10 billion years from now, our Sun would have kind of burnt all its hydrogen and converted it into helium. Maybe traces of hydrogen is left. So by that time, what happens is kind of, I told you, gravity will take over again, but then the temperature is going to cool down, which means when the temperature cools down, the body of mass is going to expand. So we have to consider that point here. So the size will actually grow at that point because the temperature is falling down. Why is the temperature falling down? Because there is a lot of reaction that is taking place and there is more of helium now than hydrogen. The fusion has already happened. So there will be a drop in temperature. Then we are talking about a sizable expansion of the star. And that's what we call red giant.
Didn't you say the bigger they are, the hotter they'll be?
Yes, it will become hotter. I will tell you why it becomes hotter. It will become hotter to us with our perspective, because what will happen is when the Sun expands, right? When it reaches a red giant stage, it will take up a diameter that is going to touch Venus's orbit. So that will make the temperature, say, 10,000 times more than what it is right now. And typically what will happen is the Earth will get destroyed.
So you're talking about just the temperature on Earth, not just...
I mean, that's our point of reference, right?
No, but don't things expand when they heat up? When they get hot, they expand.
Because the
and they get
kinetic
cold.
energy.
It's just the fusion reaction we are talking about here right now. So on the surface of the Sun, there will be still fusion reaction taking place. So the temperature
The Sun is getting colder, but from the perspective
of Earth, it's getting hotter.
It's
Hotter, yeah.
Okay.
So let me go to the
Venus
next slide.
with its own heat? I thought Venus was just.
Venus is a planet. Venus is not a star. So Venus does not generate any heat by itself.
So why does the Sun feel hotter to us as it gets to Venus's orbit?
That's because we are closer to the Sun. The Sun itself will expand till the diameter.
because
Yeah, yeah.
And it's still warm.
Yeah,
It hasn't
yeah,
died.
yeah,
It's just
yeah.
not
It's
as
just
hot.
that it's in its first stage of dying.
So from the perspective of like say an IR
Uh-huh.
camera, is that hotter or colder as it's going to a red giant?
I would say it's colder from Sun's temperature point of view. Yes, it's colder. So this happens when the core is exhausted of hydrogen. So
So, sorry,
Uh-huh.
I'm confused.
Uh-huh.
So, is this stars are considered gas?
yeah, they are just volumes of they start off as gases,
Mostly gas.
mostly gases.
Mostly gas.
Yeah.
So as they get colder,
Mm-hmm.
their volume gets.
The proportion between
So it's like
hydrogen and helium
equals-
changes. That's the thing. So when the star begins, it's all hydrogen and little helium, and when it progresses, when it dies, it's going to be more of helium than hydrogen. It's not like helium cannot be further fused. I will come to that, but it doesn't happen in case of our Sun because our Sun is a very average star. So you don't have the
Average.
yeah.
Size-wise?
Yeah,
What
size-wise.
makes a
Size-wise.
star average?
It's size-wise, yeah. Size-wise and temperature-wise.
Sorry, I didn't know.
Yeah, but it's like everything to us, but it's from a universe point of view, it's not that big a star.
But if the red giant is because the hydrogen has been exhausted, which means that the fusion is no longer happening, then why is it still warm?
No, fusion is still happening. It's
Oh.
just that at its core, it's not like it's run out of hydrogen.
At its
Fusion
core,
is still
but-
happening. Fusion will continue to happen till the point it dies.
Oh, just not as much.
Yeah, it's not as much.
Oh,
Yeah. So as I told you, these two forces will the gravitation and the energy are inversely proportional. So what happens is the core begins to collapse because the core is running out of hydrogen. So the core will start to collapse. That's why like the temperature will increase and the pressure will increase gradually, not at the red giant stage. It begins at the red giant stage. So this is again, this might happen, may not happen. In our sun's case, we don't know, but something happened and we are here and the Earth is existing as a planet and we are all living. So some other star died and that's the reason we are here. I'll tell you why. I will come back to that. That's a different topic. So helium again fuses into carbon and energy. But again, the extent of, if you see the MEVs produced, it's lower because hydrogen fusion into helium gives you the maximum amount of energy. This doesn't give you that much. So if you see, this is what happens after the red giant stage. So as I told you,
What did you say forces helium into carbon and energy?
Let me go back.
Like
I
what,
see how much energy's out, but what forces it to do that?
what triggers that reaction?
Again, the
I know,
heat.
but what triggers fusion?
Yeah.
Again, the heat. When it's all helium, helium fusion will actually trigger it.
Yeah, but you said when the star burns out, we have mostly helium left over.
Uh-huh.
So there's no more heat. What's forcing the fusion?
It's still hot enough. It's still hot enough. It's 100 million degrees.
So it doesn't die when all the hydrogen goes away.
It
dies
again.
when the helium has been refused back to carbon and energy?
This happens only in some kind of stars, and mostly in some of the stars, this is an intermediate stage where it doesn't go to the stage at all. In some stars,
So it's a multiple process.
yeah. That's why I told you there are two scenarios here: one for sun-like stars, another for stars that are bigger than the sun. So stars that are bigger than the sun continue to actually fuse a lot of times. I'll come to that slide. I have a slide for that.
These would have that part
Yeah.
of the carbon and energy.
Yeah, these are typically sun-like stars. This scenario might happen, might not happen. We don't know, but this is as far as they can go. Sun-like stars.
So was the hydrogen fusion at 15 million degrees? So was, sorry.
Yeah. Let's go back to that slide.
Oh.
Yeah, that's 15 million degrees.
So the hydrogen fuses at 15 million degrees, but then the helium needs 100 million.
That's
degrees.
because
So where's the heat come from?
Yeah, that's what I'm like
Yeah.
using the track in there. Like, how does it get hotter right at the end if everything's dying off?
it gets hotter because the core begins to collapse. That's the scientific explanation here. So when there is no energy that is emitted from the fusion, the gravitation takes over and then the contraction begins again. The core is running out of hydrogen.
Contraction, I don't understand what causes the heat.
Kinetic energy.
Can gravitation?
Gravitation?
Yeah.
So there's more
Yeah.
pressure.
Yeah, more pressure, heavier. I'll tell you why it's heavier.
Yeah, why is it heavier? It's less
Because
mass.
there is more and more of mass contracting and contracting and contracting. It's trying to implode. At one point, I'll tell you there is a slide for that. If you take 1 teaspoon, it will weigh 1 ton.
Is it a black hole?
Yeah, it's something like, it's just before a black hole. There is a stage called neutron star. I'll come to that.
Oh my
Yeah,
goodness.
so
Yeah.
stars
It's
that
all
black
life cycles.
hole
Yeah.
can form.
Yeah.
I'll come to that. So this is what happens after the red giant stage. Again, in red giant, we are talking about at least a million years in red giant. It's a very slow process. It doesn't like happen in 10 years or 15 years or something like that. But the good news is the moment the sun reaches red giant, we're all dead anyways. So yeah, so it doesn't matter what happens after that. No, I mean, we have a good 10 billion years to worry about that. So we should be more concerned about asteroids hitting us or something else, or solar flares hitting our atmosphere. That's more likely to happen than this one. Yeah, or coronavirus. So what happens after the red giant stage is we kind of reach to a stage where the outer layer of the sun like cannot hold up at all, and it gets spewed off as an explosion, and that's where you get these nebulas. So what you see here is called the planetary nebula, and the Earth was formed in one of this reaction. So a star actually spewing off its outer layers, and then what happens is the outer layer will get like fused into other elements. You have carbon there already, which is the most essential element for human life, I would say, after oxygen. So we are all built of carbon.
So, how do we know that Earth was formed?
That's the only way planets can form. This is the only way any planet can form, not just Earth.
And the difference between planets and stars?
Oh, this is
Was this discussed? Sorry.
okay. Planets, they don't emit their own radiation. It's not an energy source. They just receive energy from other stars.
Parasites.
Pardon?
Parasites.
Parasites, yeah. You could say parasites, yeah.
Alright, that's only if it feeds off, parasite feeds off something else. We don't necessarily feed off the sun, we just use the energy that's received.
Yeah.
We're kind of feeding off.
Isn't it a star one of the planet?
I don't think that
Star?
Yeah, a star is the next cycle after a planet. I mean, whenever the Death Star just shoots at it.
I don't understand your question at all.
No, what I mean
Star
is.
Wars reference.
Yeah.
Oh, Star Wars reference? Okay.
No, what I mean is
Existence of the sun.
when a planet dies,
It's
I
like
don't
we're
know
not
how it
growing
explodes, whatever.
stronger.
Doesn't it become at that point a star? Or no?
No, it doesn't.
Sun would
We
go
are
It doesn't.
growing stronger, right?
A star can die and become a planet, but not the other way around.
Oh, okay.
Yeah.
A star can become a planet and not a planet.
I mean, star can break down into several fragments, and those fragments can become planets or asteroids.
Okay.
Whatever.
But
Okay.
yeah, the other way around, you still need hydrogen clouds and helium clouds to again fuse together. So it doesn't happen the other way around, as far as I know.
So then this explodes,
Uh-huh.
and then it starts.
We are just talking about the outer layer exploding here. So if you see here, this image is a perfect example. You still have the star, which is very, very tiny here.
Oh,
It's still the star. The star is not dead yet.
okay.
Um,
The outer thing.
Yeah, the outer thing is coming out, and we have several elements, and there are other planetary elements that are forming out of the planetary nebula. Nebula is just like the infancy of planets, I would say.
So does that right hand picture, does that happen really quickly? Like, is that like a flash and then all of a sudden planets are there? Or is that also?
No. It takes several millions of years
That
again.
also
Yeah,
takes millions.
yeah. I mean, in astronomy, million years is like a minute.
Oh, okay.
Yeah,
It seems like it would just fly off.
Yeah.
Or something, I don't know.
yeah.
These are all simulations, like we haven't seen.
No.
So
Oh, it's a simulation, that's not a picture from
no,
the
it is a
Hubble.
picture. It is a picture from the Hubble.
Oh, okay.
It's from some other galaxy, some other place, but it's a picture.
Oh, it's real.
Yeah, it's real.
That happened like billions, millions of years.
Yeah,
Several light years.
That's
Yeah.
cool.
So it doesn't look like this.
Like, yeah.
it might change. It might change from what it is right now. But I wouldn't imagine it will say if you take this picture today, it will be that different because we may be 100 years off or 10 years off, which is nothing.
So what's the difference between the three nebulas?
There are all different nebulas. That's it, from different galaxies.
So are these like stages or different types?
No, the different. I mean, there are three different pictures of planetary nebula. That's it. So they each have a name. If you see, this is called the Ring Nebula. This is called the NGC 2440. This is called the NGC 3132. So NASA names them differently.
And why does the one in the middle look so different than the
I will come to that again. That's a good question. Hold that thought. I will come to that.
So now the sun has exploded, but planets are forming. Is that what's happening?
Yeah, planets.
Are beginning.
This
to
is the
form.
incubator for planets.
So the sun's kind of gone, right?
We are talking about star, not sun. So yeah,
Wait, star is a sun is a star.
sun is a star, but sun is the star closest to us.
No, but I'm talking about any other sun. I mean, a star is a sun. That's
Uh-huh.
cool. So this is a star
Uh-huh.
with planets forming around it, but the star just exploded.
Star just exploded. The star will no longer exist.
So it's got planets around it,
So-
So
orbiting around it.
I'll tell you, we were not formed from the sun. Sun is our closest star. But we were formed due to a death of another star.
So our sun was formed from another
Exactly.
star.
Exactly. So we were not formed from the sun.
But the sun also was formed from the death of another star.
Yes, exactly.
Okay.
Exactly.
So a death of a star can generate either another star or a planet.
Or both.
So-
Or both.
So
So
by
what-
this logic, then like there can be exponentially growing of solar systems, right? 'Cause
Yes, that's what NASA says. There are multiple solar systems even within our Milky Way galaxy.
So even if like, let's say you have two solar systems formed from
Mhm.
an exploded star before it, and then you take that over billions and billions and
That's
billions
why
of years, then
That's why
we approach.
we have SETI.
Yeah.
So SETI is it's called Search for Extraterrestrial Intelligence. They strongly believe that there is another human force out there somewhere. I mean, outside our solar system.
just by the
Then-
probability.
yeah, just by the
there's
probability.
so many-
Are you familiar with the Drake's equation?
No, I'm not.
We'll talk
Yeah,
about it.
yeah, we'll talk about it later. I mean, this is a huge topic. I don't think we can cover everything in 25 minutes, but
Only
yeah,
the universe that
yeah,
we're talking about.
yeah. So, this stage here, sorry, I have to go back to the previous slide. So, if you see the white star that's left behind, it's called the white dwarf stars because the surface, most of its surface is blown away, and what we have is like a smaller star. So, the planetary nebula will have it in the center typically. So I was telling you this reference. The size of the Earth with the mass of the Sun is like if you compare it, then you weigh it in a teaspoon, then a teaspoon will weigh 1 ton. It's just a gross comparison that they're equating it to. So that's 1 million gram per centimeter cube. So this is the stage called white dwarf. White dwarf stars are stable, are better stable than the red giants. So, like it's going to stay another million or billion years without going further. This is one scenario. This is what probably will happen to our sun. It will get into white dwarf and stay there forever. So it's like it's not a catastrophic death; it's a graceful death. That's what I meant. White dwarf is like at that stage, you can classify the star as dead, but still something is there. Now coming to the other scenario, we are talking about stars that are much bigger than the sun. What happens there? Like that's where you'll get other elements as well, not just carbon. So they just continuously keep fusing. So they reach the red giant stage, and then they see and they collapse one by one. So I'll go to the next slide. If you see, so first is the hydrogen fusion, next is the helium fusion, next is the carbon fusion. Our sun does not go through these things. So we were not formed from a star that is of sun size. So we were formed by something much bigger than the sun. So what happens is helium fuses into carbon, carbon fuses into oxygen, oxygen fuses into neon, neon fuses into magnesium, magnesium fuses into silicon, and then once it hits iron, it stops. Iron cannot be fused further. So what happens is iron is pretty heavy in that stage. So it's the most stable element known to us so far. You cannot make radioactive iron, I guess. What happens is we don't produce enough energy, so gravity takes over. So the star again starts collapsing under its own weight. So what happens after that is one of two scenarios. So the first scenario is called a supernova. You will have a gigantic expansion of the star, like it just explodes with nothing left behind except a black hole. The black hole is so strong that it can pull all the light towards it, whatever comes towards it, millions of light years away. If you're anywhere, even in the proximity of a black hole, then you'll be sucked in. The other scenario is where what happens during the supernova. So there's a lot of gamma radiation there because it's a big explosion. So it cannot be seen by, it cannot be perceived by the human eye that easily. But then we are talking about a lot of energy. And what I have learned through the NASA slides is if we happen to live anywhere close to a supernova or nova that is even taking place in another galaxy from us, that will still impact us and kill us. That can happen. But these are, again, we are talking about astronauts. The time in space is different from the time we live in as humans. So probability is low. But if it does happen, then the gamma radiation from that is good enough to destroy and cook the Earth's atmosphere. This was observed in another galaxy. So if you see after the explosion, the quantum of light that's shown in the picture. So this was observed from one of the supernova incidents from an Anglo-Australian observatory.
What's the arrow pointing to?
That's the star that exploded.
Oh.
It's this way. The image is this way.
It's before
Yeah,
and after?
yeah, before and after. Yeah. So these are some of the X-ray images of supernovas that are captured by NASA. It's their stock images. Like you can see from what technology did they use to capture this, because it's not like it's not in the visual spectrum. So again, from an optical point of view, you hardly see anything. You just see some clouds. From an X-ray, it's much more evident that it happens. This is a supernova called CAS-A, which is 10,000 light years away, and the diameter itself is like the diameter of the supernova is 10 light years in diameter. So what's left after the supernova? Again, two kinds of scenarios. So the first scenario is the star is so huge that something will be left behind after the supernova stage. So a body of mass called neutron star would be left behind. The other scenario is the star is just not enough to have any core left. That's when a black hole forms. So we have dealt with this scenario already. The first one is like it's a pretty small star if it becomes into a neutron star. We call it a neutron star because there is nothing else except neutrons left in that place. So that's how we get the other elements. You form neutrons, electrons, and protons. So you get all these three and you get other elements in the periodic table. They're typically only 10 kilometers across. And black hole is that scenario where the core is hopelessly bad that it is keeping on collapsing under its own weight. So it will drag in everything and anything that comes its way, including light. So this is about the theory part, but what is NASA doing to even track this is a story. And this is research that I'm talking about that happened last year in November. So this is pretty cutting edge, pretty recent. What NASA has discovered is like we don't even know of a molecule on Earth called helium hydrate. Helium hydrate is a transient molecule, and they say that's the first compound molecule that was ever formed in the universe. And usually helium is an inert gas, so it's very hard for an inert gas to form a compound. We have not heard of helium hydrate on Earth. But then NASA has confirmed that due to the pressure conditions and the temperature conditions in the stars, like this transient compound is produced. So what happens is whenever fusion happens, helium is hydrogen is converted into helium. This is a transient compound that takes place in the process. And the presence of helium hydride is a function of the state the star is in right now, like whether it is in the protostar phase or the living phase or the red giant phase or the white dwarf phase. So by the amount of helium hydride concentration, you can determine that. That's what the research is telling. And they are determining this by the wavelength of light that it emits. So they are consistently monitoring the wavelength of light it emits. Typically, it falls in the IR region. So we will not be able to monitor it visually, but we have other telescopes to do it. So this is one such image. So this was taken using the Hubble telescope. So if you see, this is a planetary nebula, which we discussed before. And the surface temperature of the white dwarf star in the center, if you see here, this is the actual star. So we are talking about 190,000 Kelvin. So if you see, this shell has abundant helium ions and hydrogen ions that can react to form a helium hydride ion. So we are monitoring the helium hydride ion. This is the technology we use to monitor. Hubble is very good for visual elements and capturing photographs and so on. But when you hit helium hydride, it emits everything in the far infrared region. So we kind of don't have any telescope that is readily available to capture that from the Earth's surface. So what happens is, our Earth's atmosphere is filled with water vapor, and the water vapor is so thick that it blocks most of the IR radiation that's coming to the ground. So what we do is, we use either the telescopes that are taken to the International Space Station, but the challenge here is you have to be on different points at different times, and to economically fuse it, you have to be at the right time, at the right place at the right time. So what NASA has done is, like, they have put it on an aircraft. This is a 747 airframe. It's called the 747 SP. They borrowed it from United Airlines, and then took it to themselves. And there is a German company which manufactured the telescope, which sits in the back end of the fuselage. There's a special door to open it, and that's a telescope. That's a giant telescope that can be pointed in any direction by banking the aircraft this way and that way. So this is like this has an IR component readily built in, and also you can add and remove modules as you feel like, because this is a mobile telescope which can be configured on the ground. Some things about SOFIA is that, like, it carries a 2.5 diameter mirror inside for the telescope to function, and it operates at 45,000 feet. So SOFIA flies above 99% of the water vapor in the Earth's atmosphere. So typically the flight profile is from California, Palm Springs, California, to New Zealand, Christchurch in New Zealand. So that's the range of the aircraft to get the maximum readings out.
And they can fly for 12 hours at a time. So my friend actually is on the team that uses SOFIA mainly to do all their research, and they're studying the polarization of space dust.
Yeah. So SOFIA is used for a ton of other things, but this is specific to what I'm talking about, to measure the helium hydride wavelength. It also has a spectrometer on board, so it can analyze the spectrum from different stars and different planetary bodies. So what SOFIA observed was, in the nebula picture I showed you, if you see here, typically you get, they predicted the wavelength that is associated with helium hydride, and they confirmed helium hydride is there, and then they kind of determined the age of the planetary nebula using that. So what happens here is after the helium hydride is discovered, there is a spectral line that's shown up at the expected wavelength for helium hydride. Strength of the emission was somewhat larger than the theoretical model predicted, but that's still ongoing research. And we have good news that we can predict the age of stars using helium hydride concentration. That's about it. I'm reaching the end of the presentation. This was, I visited SOFIA. There's a person pretty much familiar to all of us. Unfortunately, he's not here today. And we had a great time. We got to see the telescope, we got to see the airframe, and we got a good lecture there as well before going there. This was in October last year.
You didn't have a mustache then.
Yeah, I kind of shaved it off, and yeah, I represent NASA as well as Civil Air Patrol, so I kind of like represented Civil Air Patrol in that. And then Dar wanted to join because he was very interested in the telescopes and the optics part of it. Yeah.
Is there like some vibration isolating elements?
Yes, there is. That's like from a telescope point of view, you have something called a stabilization mechanism there,
Okay.
which is more of I think what's there in your digital cameras and so on.
Oh.
Yeah.
Oh yeah.
Yeah.
Cool.
Thank you so much.
Yeah.
This is great.
Thank you.
You're going to be a great NASA ambassador, I can tell.
Yeah.
That's
Thank you.
fantastic.
Thank you.
Be doing that over the next year, right?
Yeah, I'm doing that over the next year, and if I manage 4 of these, I think I can get it extended to 2021 as well,
Great.
and 22. So let's see how it goes. So this is my first start at something really, really, yeah, that's my passion, but I'm not a subject matter expert in any way.
A star is born, right?
Yeah. Finally born. And that's why we are here. The star is dead, and that's why we are all here. Yeah. Thank you, guys.
Thanks, Kailash.
It's 40 minutes, but yeah.